In this section, you will be using the 4 elementary power series. You are expected to know them from memory. But if you happen to forget, but still have the Taylor series formula memorized, you could always recreate each of these power series using what you know about Taylor. Some patterns I see with the sine series is that it starts with x, and we've got a lot of odd numbers happening. With the cosine series, we start with 1, and we've got a lot of evens happening. With e to the x, it seems to go 0, 1, 2, 3, 4, 5, and so on. And ln x, our denominators are 1, 2, 3, 4 without the factorial, matching the degree of each term. To create a new power series, we're going to use the series for sine x and then substitute in x squared. Here's the series for sine x. Now let's replace each x with an x squared. And now we're just going to simplify. And there's our new series, the series for sine of x squared. Here is the series for cosine x. Now let's replace each x with a root x. And we could simplify those exponents. To get a beautiful new series for cosine of root x. For number 3, we're not going to substitute anything different, but we are going to multiply each of the terms by an x. E to the x looks like this. And we will simply distribute the x into each term in the e to the x series. And there's our new power series for x times e to the x. 1 over x. I don't actually have a power series that looks like that, but I do have a power series for ln x. And the derivative of ln x is 1 over x. So the beauty of power series is that they are so much easier to derive and integrate than transcendental functions. Therefore, the series for 1 over x is just the derivative of each term in the series for ln x. Here's the series for ln x. Go ahead and derive each term. For our last step, let's reduce. Which gives us a power series for 1 over x. Number 5 is asking for a power series for the integral of ln x. Rather than integrating ln x and coming up with a series from that would be quite complicated. We're going to take the series of ln x and integrate it from 1 to t. And now we're going to integrate each term. To keep the pattern that this series is going in, I'm going to consider this as a group x minus 1. So when I add to the power and make a new denominator, it's going to look similar to the rest of the terms. Continue integrating. We can simplify that. And now we can evaluate it from 1 to t. Yes, you must show that subtraction. However, plugging in 1 will give us a 0 value. I believe that would be sufficient for AP grading. Now write the series one more time without the subtraction. And there's a power series for the integral of ln x. An alternating series is a series whose terms alternate between positive and negative. 3 of the 4 elementary series are alternating series. Notice that e to the x is the only one of our 4 elementary series that does not alternate. So there's actually a special test to determine whether an alternating series converges. Let a sub n be greater than 0. The alternating series has negative 1 to the n, or sometimes negative 1 to the n plus 1, multiplied by a sub n. This alternating series will converge if the limit of a sub n as n approaches infinity is 0. Note that a sub n does not include what I like to call the alternator, the thing that determines that it is an alternating series. So a sub n is the non-alternating part. That makes a sub n plus 1, which means the next term, must be less than or equal to each term before. That is talking about the absolute value of each term, not the alternating part. Determine the convergence or divergence for 6 and 7. First of all, we have an alternating series because we have negative 1 to the n plus 1. That would make a sub n, the non-alternating part of the series, equal to 1 over n. The first condition would be to establish that the limit as n approaches infinity of a sub n is 0. That is true. The next is to establish that 1 over n plus 1 is less than or equal to 1 over n. This is also a true statement because n plus 1 is greater than n. And if your denominator is bigger, then the fraction will be smaller. Sometimes it helps to just test some values though. So the series in number 6 has satisfied both the conditions for an alternating series to converge. Therefore, this series converges by the alternating series test. That is also known as AST. For number 7, yes, we have an alternating series, making this a sub n. Does the limit of a sub n as n approaches infinity equal 0? We take the terms of highest degree, and we get 1 as our limit. Therefore, we know, based on the alternating series test, that this series diverges. And you can use the acronym AST to represent alternating series test. We now have 3 tests for convergence and divergence. What are they? The geometric series test, the nth term test, which is only for divergence, and now the alternating series test.